I will speak today about the DINCAE, a neural network to reconstruct missing data in satellite images. So the state of the ocean can be inferred in different ways, about using in situ data, using satellite measurements, or using ocean models. And actually the technique to combine all these three approaches is called data simulation. I will not speak about data simulation today, but the method that we implemented with the neural network is inspired, or it's motivated by the way data simulation handles missing data. So remote sense data is generally more accurate than models and has a fairly good spatial coverage, especially compared to in situ data, but we still have fairly large gaps. As we can see here in the Mediterranean Sea, clouds can cover a really substantial part of a scene. And obviously we're just measuring the surface, and we have just a handful of parameters that can be measured remotely by a satellite. But in order to train a neural network using these kinds of data sets, we would ideally have a large collection of full images. But the sad truth is that only very few images do not have any clouds. So the idea is that we need to have a method that can be trained using missing data. And in order to make our tests, our experiments, we were looking for the longest time series of data that we have, and it was actually the GHER data set, which starts from April 1985 to 2009. And we are using data from the EGU2020, which is part of the Mediterranean Sea, so a relatively small area for this first test. And the last 50 images of this time series were removed and used for validation later on. So this is a study area. The red rectangle is the EGU2020, where we're reconstructing the sea surface temperature, and in this area we have very strong currents like the western causal current, the eastern causal current, and the northern current. So it's a quite interesting area. And the way data simulation handles missing data or data in general is governed by what's called the bias rule, where you have a prior estimate, be it a prior model forecast or prior estimate of the state of the ocean, and an observation. And the bias rule tells us how to combine these two kind of information. And if the model and the observation errors are distributed following a Gaussian probability density function, then we are ending up with these two equations, which tell us how to optimize, how to derive the mean and the error variance of the combined state, of the analyzed state. And from these equations, already quite interesting, we see if the data is for some reason missing, it's just similar to treat it as if it would have an infinitely large error. And we are not combining observations and model directly. We are instead combining the model scaled by its error variance, so divided by its error variance, and as well the observation divided by its error variance. And so this gave us a motivation how to handle missing data. Instead of working with the data themselves, we work directly. We're working with the data divided by its error variance, and also included the inverse of the error variance as an input as well. And the structure of the neural network is quite similar to an autoencoder, which has a lot of similarities to an EUF decomposition. So as an EUF decomposition, you have a step where you project an image or a data set onto a set of EUF bases, and this EUF amplitudes that you then get are some kind of compressed representation of the information inside of the original data, and from this compressed information you can reconstruct the full data set. And an autoencoder works quite similarly. So you have a input image and its error variance as its input. You are applying a series of operations, which are convolution layers and pooling operation, and then you condense information, and you are in some sense applying the reverse operation, convolution as well, and interpolation steps in order to get a full image again. The input data is not just a single image, as I mentioned before. It is the image divided by its error variance and the inverse of the error variance. We also included this the SST from the previous and the next following day in order to use the time dimension as well in the analysis. And also we include information about longitude, latitude and time. And so the autoencoder has a quite symmetric structure. The first step is the encoder, which tries to compress information. We're using 5 encoding layers, but this is a parameter that can be changed easily, and 5 decoding layers to get the full image in return. And after every convolution step, we have what is called the average pooling. So we are reducing the effective spatial resolution by a factor of 2. And in the center of the autoencoder there are some 2 fully connected layers, including 2 dropout layers in order to prevent overfitting. And then we have decoding layers, as mentioned before, in order to get the full image at the original, to reconstruct an image at the original resolution. And quite crucially, we also implemented the skip connections. So it means that the information does not have to, all the information does not have to flow necessarily to the bottleneck, but we allow also some informations to bypass the bottleneck using the skip connection. And this is quite important, and the reason that this had a quite significant impact on the reconstruction is that the information in the bottleneck actually represents structures affecting the full scene of the SST images. But there are some small scale structures like LDs, filaments, which do not affect the full images, and they would typically get lost or smoothed out if we force that all information pass through the bottleneck. So in order to allow the skip connections, we are retaining much more small scale information. And so we're training this network using stochastic gradient descent. So we are splitting the data set into mini batches of 50 images. So we're computing the gradient, we're computing a loss function over this 50 image, and then its gradient is used to optimize the weight involved in the neural network. The weight in the neural network actually attached to, in our case, to the convolution layers and to the fully connected layers. And the full data sets are used multiple times, and this is actually called an epoch. And now, quite importantly, is the choice of the loss function. And since we're not only trying to having the value of the C-surface temperature at all grid points, we also want to have its expected error. So we need to take into account the expected error also in the loss function. And there is a fairly I would say elegant way to do it, using the likelihood, using the expression of the likelihood. So what we're actually maximizing is the likelihood of the observed value provided our estimated mean temperature and mean error variance, where here mean temperature and error variance are really for every pixel, for every location in space and time. And this equation that you see here is actually can be derived directly from the expression of a Gaussian function. So it's essentially just the minus of the logarithm of the Gaussian function. So in data assimilation you often consider the error variance as given, and not a parameter that you actually optimize. So therefore a lot of terms in this cost function will just disappear because they are considered constant. But here essentially the sigma hat is also a parameter that we want to optimize, so that it therefore is also present in this cost function. And so for any mathematical detail I will refer the reader to look to the paper instead. And so this is the RMS error relative to the validation data set for different epochs during our training. And so you see that the cost function, the RMS error, it's not the cost function, the RMS error varies quite a lot. And this has to do that the optimization does not use the gradient computer of the full data set, but only over a small part of the data set. And this introduces some stochastic variations. But these stochastic variations are actually wanted because they helps us to not get trapped in a local minimum. But they're also enhanced in our case because we're computing the cost function, the loss function, only over a small part of the data set. And what we did in order to control this fluctuation, we actually computed the average reconstruction between the 200 and 1000 epochs, and that's what you get. And the RMS error that you get is of this average is the red line, and it's actually, and we were able to show that it's actually better than the other method that we're using, DINCAE, to reconstruct cease-fast temperature. But the quite interesting aspect is we're also providing not only the cease-fast temperature but its expected error variance. And what you see here is a plot of the true, so the validation, cross-validation, cease-fast temperature, and the reconstructed cease-fast temperature. And the reconstructed cease-fast temperature does not use this validation SST. So ideally you would expect all temperatures scattered here on the diagonal line, and if they are not, we would hope that the error produces a larger error. So, and the error is here coded in color. So typically we see indeed that if the reconstructed temperature is not similar, is different from the true SST, we also tend having larger errors, larger expected errors. And if you compute what is sometimes called a scaled error, so if we compute the difference between the predicted temperature and the measured temperature by the satellite divided by the predicted error, ideally we want to have something which follows a Gaussian, a normalized Gaussian. And that's what is shown here. The normal distribution is the orange line, and the blue bars represent the scaled error. And we are seeing quite interestingly that they are actually fairly similar. That so we are slightly underestimating the error, but we are having still a quite reasonable error estimation. And this for me was quite an interesting result, because a lot of other data analysis techniques like optimal interpolation or ensemble Kalman filter, so typically the expected error that you get from optimal interpolation or the ensemble methods are often quite uncertain. So the so that we can here have a method that produces fairly reliable and robust errors, which are actually quite interesting result. And here are some satellite images. So the first image on the top row is the original SST, but we added clouds to it and gave only the SST with clouds to DINCAE for reconstruction. And that we will see, that's the image on the right on the top row. It's a DINCAE SST, the reconstruction, and it's actually quite similar to the original SST. Some differences are obviously there, but the the reconstruction is quite realistic, I would say. And the row below is the expected error and the DINREF reconstruction, using either all data or just a subset. So DINREF reconstruction is a bit more smoother than the DINCAE reconstruction, which will also translate to the RMS error, as we will show later. And the expected error is obviously quite strongly related to the presence of clouds, but the values that we have seen are quite realistic. Here's a reconstruction for a different time instance, where we see that, for instance, other techniques like DINREF somewhat underestimated the temperature in this area, and for this time instance. We also validated the method using in situ data from the World Ocean Database, and we were able to show that the RMS error and the centered RMS error are a bit better using the DINCAE reconstruction. And so, we were also looking to the variability around the seasonal mean, and so it was quite interesting to see that the reconstruction has a fairly realistic variance around the seasonal mean, while DINREF did underestimate a bit this variance. So this is also quite interesting result, that the method is not only more accurate but also has more variance than another reference method, DINREF in our case. So I think we demonstrated a practical way in order to handle missing data, to train a neural network with missing data. And it's fairly simple. You're just using the data divided by the expected error variance, and the error variance for missing data will just be infinitely large, and using this inverse of error variance as well as input. And you can use a cost function that not only gives you a typical regression value, or typical estimate of the data, here temperature, but also its expected variance by using maximizing the likelihood actually of the observed value, and therefore letting the neural network also to produce an error variance as its output. So we think that this method worked quite well for satellite data, and it also were able to retain a significant amount of variability in the original data. So the code itself is open source and available on GitHub, and the paper in geophysical model development was recently accepted, and you can check it out at the link provided here. And the paper is open access, so it's quite easy to access it. Okay, thank you very much.